So now that we get past the process control, just talking a little bit about some of the features in a controller to look for. And a lot of this is compatibility. So primary inputs, and again, I know this is pretty straightforward, but it never hurts to kind of think about these types of things. And that is, what are the types of inputs the controller can accept? Popular inputs would be thermocouples, and there's a variety of different types, and J's and K's are popular ones, but there's certainly some other options out there. As Derek talked about, the RTD inputs, and then also the linear, or you might see it as analog or even a continuous, it might be called input. And this is basically a current or a voltage range. Commonly we see 4 to 20 or a 0 to 10 volt range. But it's important to note that the controller is looking for an input, but that doesn't always have to be temperature. Especially in the way of a linear input, the controller sees a current or a voltage value. It doesn't know whether you're talking temperature, pressure, flow, humidity level, and I'm sure there's other ones out there. It's seeing a current rating, and it's trying to understand or trying to extrapolate that to something that it can work with. And that's where we get into scaling inputs. So the first thing really that a customer should do is it should tell the controller, what is my input? So here's a little snapshot. This is actually a large list out of the 40 series controller, but just a snapshot to kind of get a feel for what the controller is expecting. This is where you assign it and say, hey, I have a Type J thermocouple. And this is in C, so this is my range that I'm working with. So once you set that, now the controller knows, okay, this is what the input is. These are the bounds that I'm working with. That's very important for linear inputs because, again, if you're setting a 4 to 20, for example, you know, and a controller sees a 4 milliamp signal, well, what does that really mean? Or what does a 10 volt mean? That controller doesn't really know what you're trying to tell it. It just knows I'm seeing 4 milliamps. So when you scale the input range, you're basically telling the controller what is the bounds that I'm working in. If I see a 20 milliamp signal and you set it to a 500 degree scale, now it knows, okay, I see 20 milliamps, this is a 500 degrees. Or on the low end, this is a 4 milliamp, okay, that's 100 degrees. So now the controller knows what that signal you're sending or what you're telling it to do with that information. So this is very important. Again, if you're getting customers that are calling and they have some strange things happening and you know, they're expecting one thing to happen and something else is happening, it's very important to just have them look at how they're scaling those inputs. Maybe it's just a matter that they didn't scale them and they're running off default parameters, or maybe they did and they just chose too broad or too narrow of a range. So you can make sure that they're actually thinking, you know, what do they really want that controller to do when it sees that linear input. Then we talk about primary outputs. So again, you've seen all the build tables. You know, a lot of our controllers come with capabilities for relay, SSR drive, TRIAC, and analog outputs, to name some of the more popular ones. But really, you know, what does that mean, or what is that actually trying to do in terms of driving the output? And that's what we'll talk about here in a minute here. So the first is a relay output. Really straightforward. It's really just an on-off switch. We think of just like a light switch. Relay is either on or it's off. The controller is either saying, give me power or don't. So if it is calling for power, you're giving 100%. If it's not, you're at 0%. So again, very straightforward control. And an important thing to note here is the controller's relay outputs are usually rated very small amperage, so they're not meant to direct control a heater. You need some sort of power control involved in there to actually do that switching. The relay is more or less telling that power control when it wants power and when it doesn't. Now the exception to that, just to give a quick shout out to a control here, is our 2110, where that has a special high amperage relay up to 20 amps, where it can actually directly control a heater without that extra contactor or SSR or whatever else in power control. It can do it directly through that relay output. Another type of output is the SSR drive, and essentially it's operating under a very similar premise as the relay, but it's a solid state relay, so it acts very quickly, and it works by driving a low or a high voltage. If you want the controller to be off, the power controller to be off, it would send a low voltage, about 0 volts. If it wants it to be on, it would send a higher voltage, somewhere in the order of 24 volts. So it's driving the SSR based on what that output is, based on what the demand signal is. So when it wants power, high voltage. When it doesn't, low voltage. Now, because the solid-state relay doesn't have any of those moving parts, you really get a lot of rapid switching of on and off. So you can follow a number of zero-cross methodologies. You can get very fine-tuning. Even though you're still doing an on-off type control, you can still fire in different configurations, much like Derek was talking about earlier with the dot firing or the time proportional. You can still get very, very intelligent logic on those firings to get more accurate control. You also have TRIAC output. This really isn't too popular for what we see. A lot of our power controllers are basically an SSR or SCR, but your customers might see TRIAC type loads in the field. And a lot of times this is a more of a unique type of load. Dimmer switches, different types of AC motors might use this. So not something we necessarily see very frequently, but it is important to know really what that is. So just some of the questions we see a lot is what's an SSR and what's an SCR or TRIAC? So talking very high level, SSR is really just a solid state relay, and it's just an electronic switching device. So much like your mechanical relays that have moving components, this is no moving components, so it's just a solid state version of that switch. An SCR is a more involved and a more complete assembly of that. Different firing boards and trigger boards can be included with that. The important differentiation between the SCR and the TRIAC is that an SCR only switches current in one direction. Now, obviously, we have a lot of AC loads that we do, and we still offer SCR. So how do we accomplish that? Well, we do that by having two inverse parallel SCRs together. And this picture just kind of paints a little more description of what that means. So in an AC signal, obviously, you have polarity in one direction, and then it returns the opposite direction. So one SCR by itself could only handle that one direction, but with the inverse parallel, now you can fire that full cycle. So you can get the full sine wave, much like Derek was talking earlier with that different sine waves. You can get the full stretch of that with using this kind of configuration. Now the TRIAC essentially accomplishes the same thing, but it does so in one component. So one component is actually switching in both directions. So this actually lets you kind of control how much current is flowing through. It also lets you kind of do some limiting capabilities, and again, that's why you see it in dimmer type switches, is you can kind of throttle that output and handle the different oscillations that are happening. The downside there is because it's switching and one component is doing everything, you might not always hit it right at the 0 point, that you can get some noise when you're switching between the different polarities. And then moving on, so our analog output is the last type. And this is really, it's not just an on or an off. You can, again, we talked about that 4 to 20. You have that whole range where now the controller can interpret, what is somewhere not only just at the low or the high end, what's something in between that you're looking for. And that's where you can get much finer tuning, proportional capabilities. And I won't dive too far into this. I think this is something that we can move into one of our future trainings and really get down into some of these different firing methods. But just on the surface, it's using that proportional control, you can do different things with the time base to get a finer tuning, more accurate control. And in dot firing, you can really shrink that time base down to very, very, you can even see here one cycle or 16.6 milliseconds in a 50% control. You're basically firing for that long and then off for that long, firing for that long and then off. So you're very, very quick changes in time and power. So that's how you can get very, very tight control in some of these applications. And again, depending on your application, that might not be necessary. If you're talking about a water tank, sure, that's pretty valuable. If you're talking about that's not very valuable. If you're talking about a very dynamic process, then that's where you start to really see the benefits of that tight control. And we also talk about the phase angle firing. So again, Derek did a good way of setting this up and talking about it, where now you can actually switch power anywhere along that AC signal. You can cut that sine wave up and limit, so you're not effectively getting a full 100% power for different time stretches. Now you're chopping up that wave, and you're actually physically limiting the current that's passing through. So you're going to see phase angle in different types of current limiting and soft start applications. But the downside, again, is you have those harmonics because you're flipping power right in the middle of it actually conducting. So that switch of power at that point leads to that noise and that harmonic distortion you might see.